We introduced quantum L carriers under in-plane magnetic field previously, and in this case the Hamiltonian is given as simple term H0, which includes the kinetic energy part, and quantum confinement, which means this barrier and well potential shapes, and the others are from in-plane magnetic field. And those are the case when magnetic field is along g-axis, and we set the quantum well direction, and the barrier well barrier this direction is set to be y-axis. So quantum confinement is defined along y-axis, and xg plane is quantum well plane. Yeah. So in this case, we set this as H prime, difficult part. We apply the perturbation theory. So the energy En, N is the quantum number. Quantum number could be 1, 2, 3, and so on. But here in this paper, we call the state as ground state, first excited state, second excited state. So this is actually same with n equal 1 state. So this is same with wave function when n is 1. So this is, in the case of the infinite barrier problem, previously we solved the wave function like this way. So even parity solution we have for the lowest state like this. Yeah. And this one actually n equal 2. So n equal 2 is the first excited state, so that electron is at the lowest energy state, at the ground state, and it is excited. And then second excited state is this one. This is when n equals 3. Alright, those are listed here. Okay. So energy is also set here. And these are the solutions for H0. Okay. So simple part. And those are actually E0, E1, E2. Actually, those are more specifically the solution without perturbation, right? So this one. So in the paper, actually, we just used E0, E1, E2, and then we apply the perturbation. We calculate this one and this one. Higher order term is ignored. So En1 is given like this. En2 is given like this. We just apply this idea into these mathematical calculations. Okay. And then the actual calculation is given here. Quantum carriers on the in-plane field. These are actually also given in homework problems in the end of the slides. So this is the solution for H0. Okay, wave function and energy. And this is the correction part. Actually, it is supposed to be E0 and first order correction, but instead of energy, in the research paper of physical E, we used epsilon, to indicate the energy correction. Okay, so they are just the same. We put the H prime like this. We know that this one is even function. So even function here, and this is odd function. We know that it is supposed to be 0 if we go through integration. So this one only survives. And those are not related with the integral, so it goes out of here. And then this one should be integrated. So this is actually same with the cosine function here, another cosine function here. They are multiplied like this. Cosine square L phi y 10y square. Right? Yeah. So then this one is actually just the same with this. Okay. So can you calculate this? Yeah. This is the partial integration from high school. Yeah, mathematics, right? So I think you can do it, right? Well, anyway, this is simplified like this way. We didn't go with this calculation yet, but we only calculate when I is 0, the ground state, lowest electron energy state. We calculate that. Second correction is so for Korean students, you can report to the Korean speaking YouTube video. Then you can also check out a little bit more details. Okay, because magnetic field is another very important problem. It won't be discussed that often in other classes in our school, but in some of the research papers you will see. So this is actually quite interesting problem. You might apply this idea into new materials, then you can have quite good research papers. Anyway, second order correction. This is just the same with this issue. Second order correction. Like this, and this is just the mathematical definition of second order correction. So for lowest energy state, so lowest energy state, and k equal 1. E1 is the first excited state, k equal 2, second excited state, and so on. And usually, surely for infinite barrier problems, there are infinite number of quantum numbers, but in conventional semiconductors, you only care zeros, the lowest energy state, and first and second excited state. That's normal case. And the higher energy states are usually not, measurable or not available in most of semiconductor structures. Then we apply when k equal 1, k equal 2, then k equal 3, it will be ignored because it will be smaller. And also, if you compare these two, we know this is actually 4E0, right? 4 times larger than the ground state, 9 times larger than the ground state. That's what we calculated before. Then it will be much smaller than this one. This one is much larger. So we will ignore this part too. Surely you can calculate this. It's not that difficult, but just to catch the structures, let's ignore this part. So let's simplify it like this way, right? Then this one we need to calculate here. So yeah, ground state, first excited state, H prime is included into here. Then we can see that this is even function, this is odd function. So this is even function, so it will be integrated to be 0. So this one only survives. So others are just not relevant to the y dependence. So we need to calculate this part. This is defined by y10. So y10, what is that? Y10 or y01. This is just the same with wave function. Yeah, zeroth order. This one. Then y. Then yeah, surely this is zeroth order and zeroth order. And first excited state, ground state. And then integral dy. So this one is this one, right? Then the energy correction is now summarized. And this is actually taken from the research paper. This is just the same. This one is here. First correction, this one, and then the others, the free energy, kinetic energy only, because no potential along xy plane. So kinetic energy in xg plane, quantum plane, right? So the kinetic energy along z-axis, kinetic energy along x-axis, right? But this one actually m perpendicular. M perpendicular means because magnetic field is applied along g-axis like this. Okay, so this part is the effective mass along g-axis. Okay, this one is effective mass along x-axis. Well, you will see that this mass is changed like this. So you will see why, I mean, based on the research paper. If you read through the paper, the effective mass is changed, especially the original effective mass without magnetic field, the case without magnetic field. Magnetic field is usually called P field because magnetic field is indicated by B, alphabet B, and then it is changed by this amount because of magnetic field. Actually, this is because when you consider the xy plane motion, if it is free, yeah, carriers can move around. But when the magnetic field is applied, the magnetic field is usually move it slowly along x-axis. So original carrier motion is changed. Okay. It is called as effective mass anisotropy, something like that. Yeah, you will see that in the homework problems. This is actually very difficult problem. Yeah. So please, if we have spare time, please read through the research paper. Yeah, I introduced previously for this problem. So everything is actually copied from the paper. You know. The final topic is variational method. And this will be, yeah, let's go through this because, yeah, next week we'll have final exam next Wednesday. So in that final exam, you won't see this variational method there. So the final exam covers only up to the perturbation part. Okay, especially please solve the homework problems yourself carefully. And one of the midterm exam problem will be repeated in final exam. So this is just the introduction to variation method. You can sit back and relax. So there won't be any homework problems or final exam problems related with this variation method. But this is very useful in calculating semiconductor wave functions. In semiconductor softwares, they are already using this variation method. So I mean, you won't see many research papers anymore because it is already saturated, it is already well done in terms of research. But through how it goes, so variation method is an extremely useful approximation. Many of the Hamiltonian cannot be separated into a solvable part, H0, and perturbation part, H prime. Cannot be separated. Even separating those is difficult. For such cases, there is no good starting point to apply the perturbation theory. Yeah, we cannot separate this, so we don't know how we define H0. So no starting point at all. Starting point was H0 in the case of perturbation theory. The variational method can be used to solve such problems and many others where other approximation methods are too difficult to employ. The principal ideas is like this. Let's consider the finite variable problems. We solve the wave function like this. The lowest energy state. In the middle, it is cosine function, and then this side and this side exponential decay. That's what we solved previously. And let's say it is this one, pi flat. In application, most important problem is the semiconductor devices, especially quantum well, under electric field. If you apply electric field, the energy, this is conduction band actually. Conduction band is tilted because of electric field. Okay. And then the wave function. Let's say this is electronic wave function. Okay. Electron wave function. Electron. The electron prepare the lower energy side. So wave function is somehow accumulated toward this side because potential is lower here, right? Because of electric field. Then we approximately anticipate new wave function. This is new wave function. with electric field. Let's say E field long is electric field. Then the original solution, this one, without electric field, and then let's just presume that it is, modified by this exponential function, exponential minus beta g over L. Let's say this is g direction. Let's say this is g equals 0. The contomal center is g equals 0. Then if we say like this, if beta is positive, for example, then original flap function, when g is larger, beta is positive, then this will reduce the wave function, right? So in this case, when beta is positive, wave function is reduced on the positive side of g, so it will be something like this, right? When beta is positive. So in our realistic wave function of this one, the shape indicate that beta is negative, right? Yeah. And then this is suggestive wave function, and then we just apply it into here. This is the calculating the energy. Let's say Hamiltonian is very complicated, and then wave function we just anticipate the wave function to be like this, and we put it here, plug it here, and then we calculate. And then wave function is just arbitrarily chosen like this, so we didn't normalize the wave function, so we don't know whether this wave function scale and the integration, it is not one actually. We didn't go through normalization yet, so because of that missing normalization factor, we add this. So we just calculate this, then this is actually function of beta, right? We didn't fix the beta yet. Let's say beta is variable parameter. We just calculate this as a function of beta, then as a function of beta. So this is very useful problem, because
then we just choose the minimum value.
Semiconductor devices are always under external electric field.
That's the idea.
When it's tilted, it means electric field is non-zero. And PIN diode, for example, you have multiple contour. This is the backbone of semiconductor devices. We have electric field here. And then wave function is not at the center, it is somehow tilted along the lower energy side. Hole is tilted along the lower energy side, like this way. Okay? So it is very practical problem. So basic idea is, let's say we have very complicated Hamiltonian. We don't know wave function, so we just presume wave function is like this. Beta is unknown parameter. We call it variable. Beta is variable. We just put it into here. So this is the idea. And the H is here and here. Actually, new potential, and this should be proportional to electric field, and G. Actually, there could be G dependence sometimes, okay? And there could be additional quantum confinement potential, because there's some area is quantum, some area is barrier. So this might be simple or complicated. You can choose depending on your own device structures. Sorry. And basic idea is, this is the structure for calculating energy originally. Okay, if the wave function psi is correct, but we don't have any correct psi, We don't know how it goes. So we just apply this idea. We just choose minimum. Okay, because the nature always prefers the lowest energy. Okay, so basic idea is we just put this into here. We just put this Hamiltonian into here, and then this energy is actually a function of beta. So this is not just fixed value, it is a function of beta. So basic idea is you apply this into your software, MATLAB, for example. MATLAB will calculate automatically like this. Then you just choose the minimum value. Like this. This is what your semiconductor software calculate the energy and wave function. So we have the minimum value of f beta. Then we just set this to be energy. Okay. And we just fix the beta to be beta 0. We put it into here. That's your wave function. That's what we do in calculating wave functions in semiconductors. Okay. In old days, calculating electron wave function was very important. But now it is already saturated. So actually these days, in my case, I researched this part in old days, wave functions of electrons and then photonic devices. Now I'm working on phonons, the heat transport, and heat is the last issue we need to solve, because heat is not manipulated. Electron, photon, they are all manipulated, but not the heat. So I mean, these ideas are now applying into heat in my case. But still, you will see some of the research papers using these wave functions for electrons limitedly. And then carrier decay time for a given electron hole recombination time, tau r. Tunneling time, tau t, we introduced previously. There could be electron hole wave function overlap. There could be tunneling. If they are mixed up, then total carrier decay time tau is given like this. This is the basic idea of electron hole recombination and electron hole decay. But the reason I'm talking about this is, if you calculate wave function like this way, then you can calculate like electronic part and hole part. There's electron hole wave function overlap. This is something called overlap. You will see this many times in research papers. We call it electron hole wave function overlap, MCV. So electron wave function, hole wave function, and then these are the normalization factors. And this electron hole recombination time, tau r, is just tau 0 over mcv square. Okay, this is well-known theory actually. Tau tunneling. Previously I introduced my old paper. Okay, you will see these structures too. This is the way we calculate various carrier decay time. So electron density you can see originally at t equals 0, for example. You generate electron density at a certain point, and then as a function of time, original density will decay like this, t over tau, like this. And this tau calculate this way. Sometimes you can ignore tunneling time, right? Your barrier is thick enough, high enough, then you can ignore. Then you can only consider this tau r. Then tau r can be calculated like this. That's the way we calculate carrier decay time in materials. Yeah, it looks well established because it has been studied very well for a long time for many researchers. So it is well done actually. But if you go to some other problem like heat, then mathematical structure is very simple. Then you will see it is very simple now actually. You need to develop your own equations, your own analysis tools. It is extremely hard, even though mathematics is simple. So even though you think this is very difficult, no, it's not, because it is already solved. Solution is already available. Actually, in that sense, it's a simple problem, even though mathematics are advanced. Solution is already well known. So even though the homework problem in the end looks extremely complicated, in terms of research, it is simple problem because it is already solved. So please respect someone who investigate something new, even though the equation could be like linear or simple. Okay. So this is actually out of scope, a very old topic. Decay scheme in quantum L. In any of the devices are just like that. So you have electron wave function, Hall wave function, this red line and blue line. Then electron can pass through the barrier. It's called tunneling. When the barrier is very thick, then there's no tunneling. And electron Hall wave function could be overlapped. Then there will be overlapped, and there will be emission. Right? Because of this emission, you have LED and laser. When you apply the reverse bias, this is something called reverse bias in device. The electric field is applied. When the conduction band is tilted like this, it means the electric field is non-zero. So wave function is tilted too. It goes toward the low energy side. Hall wave function also goes toward the low energy side. So lower means we all draw the curves in terms of electron. So when it's lower, electron goes to the lower energy side, and Hall has the opposite charge. So Hall moves toward the opposite direction. So in this case, barrier is thinner than before, so tunneling is easier. So whole barrier you can calculate. Oh, it is too thick. Then you can think, okay, whole tunneling will be very difficult. And you can also consider whole mass and electron mass. We previously studied the mass dependence in terms of the tunneling time, right? This tunneling time, or tunneling coefficient T. They are not proportional to each other actually. When transmission or tunneling is large, then tunneling time should be small, so it should be inversely proportional, like this, right? Yeah. Okay. Yeah, so those things are basic ideas to study some materials. For example, gallium nitride is the famous material to be used for LED and laser diodes and high power electronics. Surely you use quantum wells, and these are a little bit more realistic barrier structures. Okay, when there's no external field, tunneling is difficult. When you apply external field, sometimes tunneling is very efficient, so you will have very large leakage current because of tunneling. Well, the details are found in this paper of mine in old days. So based on that variation of method that I introduced. I calculated electron wave function, Hall wave function. I'm just showing the conduction band profile here, blue line. This is electron profile. Yeah, moving toward the low energy side. The Hall moves the other side. So electron Hall wave function are separated. So when you apply the bias, sometimes quantum will becomes flat, then electron Hall wave function overlap becomes larger. This is the case of blue LED. Okay, and this is case of green LED. Typical green LED has different composition like indium 15%, blue LED, indium 10%. These are already saturated old physics. Yeah, old semiconductor physics. Finally, please solve this homework problem. You submit this in the site of final exam. Yeah, please submit this answer sheet when you meet me in final exam. So actually, first problem is just the same with the many field application. It was already introduced in my Physica E research paper. Like a 2003 or 2004. It's too old paper. It was already introduced previously. Okay, then you will solve the effective mass anisotropy. What does it mean? Effective mass when the carrier moves along z-axis, then it is mg or m parallel to B magnetic field direction. Then it will be just the same with free electron mass. Okay, magnetic field is aligned along g-axis, then it cannot affect the carrier moving along g-axis. But when your carrier is moving along x-axis, then magnetic field is applied like this. Carrier is moving like this. Then surely magnetic field adjusts the carrier motion. So mass along x-axis, this is perpendicular to B, then it is very different with free electron mass. And we can see that their mass is different now. Their mass is different. That is effective mass anisotropy. This is actually well-known problems now. Okay, you can change your mass because of magnetic field. If we can solve this very well, then maybe final exam problem could be similar to this. It could be simplified, but you will see some similar problem. And then hydrogen atom problem. Yep, you listed up the energy values and wave functions previously, so try to solve this. Those two are actually very useful for your future research. Okay, so that's it for this class. So even though you cannot solve all those problems, still it's okay. I'm happy at least you are exposed to new problems. It might be complicated, still it is okay. But as you go older, you will be repeatedly exposed to research papers, and eventually you will understand why I was talking about these issues. That's good enough. Okay, thank you for your attention and hard work throughout this class. I know it has been very difficult. There were some period I couldn't, help you very well because of my surgery, and the topic itself was extremely difficult. I understand that. So I respect your endurance and your hard work, and your grade will be pretty good. I just care how hard you worked. It is okay even though you cannot solve all the problems. Okay, so thank you so much.